Okay, hi, welcome back. So this is the second video of nucleophilic substitutions. And now I'm going to go into the details of how these work. Now, before I go into this, I need to discuss a little bit briefly about how we represent chemical reaction mechanisms in organic chemistry. And there's sort of a few basic things that I need to go through. First of all, the symbol delta or small delta minus means a partial negative charge. So that means that any atom that has the symbol next to it is slightly negative. So we can say slightly negative. And it's slightly negative due to the electronegativity difference, which is the the model for the polarity. And then if you have this symbol, which is delta positive, it's just slightly, it means exactly the opposite, right? Slightly positive. First off. The second thing that is kind of common within organic chemistry is that we use arrows that we call curly arrows to show the movement of electrons. So this arrow, which has two barbs, right? If it has two barbs, it means that it's indicating the movement of two electrons. So we can write two barbs, two electrons. And if you have another arrow that has only one barb, then it's the one barb equals one electron. These are a little bit more uncommon in the type of chemistry we're going to talk about, but I will mention in the future. So let's talk about then, let's pick up where we were last time and talk about SN1 and SN2 reactions. In this case, I'm going to start off with talking about an SN1 reaction. And we'll recall that SN1 reactions then build on this idea that you have the dissociation, right? You have since it's a monomolecular substitution, then it's going to be some sort of dissociation, and that implies then that it's probably going to be at least a secondary, but probably a tertiary or third degree carbon substituent, I should say, substituent. And then those of you who don't know the word substituent, a substituent is anything on a carbon chain that has replaced a hydrogen. So it could be another carbon, but in this case it's going to be a nucleophile. Okay, so if we have then a tertiary carbon substituent, which is going to be a nucleophile, the nucleophile is going to act as a LG, a leaving group. An SN1 can be rewritten mathematically or with a mathematical expression or a kinetics expression, something like this. It's going to be then like, what is it going to be? It's going to be R, XCR3 or something like that. I guess there's going to be like three radicals on a carbon, and then there's going to be a leaving group, which we'll just call X. I'm not going to get into that too much, but it's relying only on that. So we can draw one really quickly then and look at what they might look like. So generally, a lot of times at least, we use the leaving group model. And it doesn't have to be this way, but oftentimes we just write an X here. And technically in organic chemistry, the X stands for a halogen. And a halogen is then going to be chlorine, bromine, or iodine. Oftentimes these are what we use as the model. It does not have to be a halogen, but for this case and for educational purposes, we're just going to use halogens because they're quite straightforward and you don't have to draw lots of complicated structures in order to keep track of them. Okay, so what we're expecting then is for this halogen to come off, right? Because the resulting carbocation is going to have its own stability due to induced induction effects or conjugation, which I talked about in an earlier video. But once it comes off, then it's going to be a carbocation, and then a new nucleophile is going to be free to move in and replace this X. So we could write a chemical reaction for this. We could write something like, where the X is here, quite simple one, plus a nucleophile, and in this case I'm going to use hydroxide as my nucleophile, and then I'm going to get my new molecule with the new substitution or substituent plus the leaving group, which will be X minus. That would be sort of the general overall reaction. But what we want to learn how to do now is we want to learn how to do this with a curly arrow mechanism, as it's called. So we want to do a step-by-step sort of visualization of how the chemical reaction is thought to occur with the best evidence available. So I'm going to draw one here, and so this usually is broken down into a series of pictures. And if you break it down into a series of pictures, then you can start with the original molecule, which is this one, and so we'll draw it here, and I'm going to use chlorine as my halogen this time. So I'm going to take this, I'm going to put Cl here like so, and then we're going to make this a tertiary substituted alkane, and so it becomes like that. Now the idea is that since the carbocation will be stable even without this chlorine on, particularly in certain types of solvents, then what's going to happen is the two electrons, remember, if it's got double barb, then it's both electrons. The electrons are going to move up onto the chlorine. And if they move up onto the chlorine, then we get a new picture here, number 2, where the carbocation has formed. And the chlorine has moved off as a free ion by itself. And since it's moved off, then the new nucleophile, the one that's present in the chemical reaction, or in the reaction mixture, then is able to move in and replace the chlorine by being attracted. So this is acting as a nucleophile, right? It's attracted to the positive charge. The double bond, the two electron pair, the electron pair here, these two electrons are able to move over and form a new bond with this carbon. And so in the third picture, then we see the finalized molecule. which is fair enough. Turns out that this part of the reaction is reversible, because this chlorine can come on and off, right? So it's not just a straightforward thing. And it's only if you have a sufficient amount of the new nucleophile that you'll get an attachment. Although this nucleophile, OH-, is much stronger than the chlorine. This part of the reaction is usually only monodirectional. Now, beyond that, we also need to have some sort of awareness of the energetics of this reaction. So this particular species, this thing that's happening in between here, this carbocation, is usually referred to as a reaction intermediate. As opposed to there's a few other things that can happen as well. But since it's a reaction intermediate, it can actually be isolated. So this reaction, this can actually be sort of like, this has its own existence. It's not something that is just a fiction, a necessary fiction to make us, for understanding how the chemical reaction occurs. It actually, it can be made isolated if you have the proper equipment. Now, if you visualize this, if you want to represent this then as a energy diagram, we have energy on this axis and the reaction progression on this axis. Then if we have our reactants starting here and our products down here, so we're assuming this is an exothermic reaction, then the reaction is going to have a certain amount of activation energy, right? So there's going to be a required amount of energy, but then there's going to be a saddle here because this intermediate is actually stable, and then it's going to go down to complete. Now, how wide this saddle is and how the difference between these different local maxima are is not important. It's just a representation. It's not. We don't have the numbers here. So this saddle then represents the reaction intermediate. And this first energy of activation is then the energy needed to get this chlorine to come off. So that's energy of activation 1. There. And then the attachment of the OH to this carbocation is going to be then sort of energy of activation 2. And that sort of summarizes the basics behind an SN1 or a monomolecular nucleophilic substitution. Then if we move on and we look at SN2 reaction, which is then a bimolecular nucleophilic substitution, we can look at that really quickly. So we have most of the concepts we need to go through this relatively quickly. So let's look at an SN2 reaction. So SN2 reactions, you can represent them with also with a kinetic expression here. So this is just going to be like Rx times the nucleophile, right? So here, both the molecules, both the original molecule with the substituent on it and the nucleophile are represented because you need both of them for the reaction to occur. So there's no dissociation. So what we need is reactant molecules actually collide. And if you have some background with this, you know that the theory goes something like this, right? That chemical reactions occur if reactant molecules collide with sufficient energy and with proper orientation. Otherwise, no reaction will occur, right? So in this case, proper orientation is actually quite important, and we'll spend a little time talking about that in just a minute. So we're going to talk about proper orientation, right? And this is going to primarily occur with like primary and secondary substituted carbons. So substituted and in this example I'm going to do it with a secondary. So let's draw one, and we're going to basically use the same example as last time, but this time it's going to be the reaction is going to proceed in a slightly different manner. So we're going to put a chlorine on here, just like last time. And remember, it doesn't have to be a chlorine; it can be other particles as well. Now let's recall then that in order for this reaction to occur, there's a little bit of a thing that we have to add here, which I began the little video with, which is then that this bond between carbon and chlorine is polar. And it's polar due to, and you represent this polarity by writing these little symbols in. The polarity is due to the fact that there's an electronegativity difference between chlorine and carbon. Chlorine is attracting the electrons to itself, and so therefore becoming negative. In this particular reaction then, it's due to the fact that this carbon is slightly positive, that the nucleophile, which again is going to be this OH minus, is going to be attracted to this positive charge. So the nucleophile is going to be attracted to the positive charge, as the name implies. And then what happens? Well, if we looked at the overall reaction, we would know that the chlorine pops off, but it doesn't pop off in the convenient way that you would think. It's not like, oh, the OH comes and the chlorine comes off. There actually ensues a little bit of a struggle here. And we know that this struggle occurs because of the way the molecule changes shape afterwards. But we can't be absolutely certain, or we can be absolutely certain that that what I'm going to draw here exists, but it cannot be isolated. So this thing is not a reaction intermediate, but is rather what we call a transition state. And so this cannot be isolated. We only believe that it exists because of what we have before and what we have afterwards. So and the evidence from before and after implies that this thing has existed, but there's no way to isolate it, at least that I know of. Okay, so in this transition state, there is a struggle between the chlorine and the hydroxide, or the leaving group, right? The Lg here, and the nucleophile. So the leaving group is hanging on. So this carbon now has too many bonds, and it is not stable in this state because it has 1, 2, 3, 4, 5, things attached to it. So one of these is going to have to leave. And the kinetics of the reaction require then that one of these is somehow going to have some sort of advantage over the other. And that usually is due to the fact that the nucleophile that you're attaching is a stronger nucleophile than the nucleophile that's leaving the leaving group. In the third picture then, the leaving group has left, and you have a carbon and CH3 and the hydrogen, and then the OH has attached. And so the reaction is over. And you get the secondary product then, which is then Cl minus, which is the leaving group. And this is sort of the mechanism for an SN2 reaction. In an SN2 reaction, as opposed to an SN1 reaction, if you look at the energy diagram, in the energy diagram, and here's the reaction progression, and here's our reactant, and here's our product. There is no saddle. The energy diagram is a smooth curve. It has one energy of activation, and that energy of activation is represented by the transition state. So this is E sub A, or energy of activation 1. You don't actually have to write the 1 because there's no second one, but I did. It's represented by this collision here, right? This is where they actually collide, and there's an exchange, and somehow one of them wins. Now, before we move on and before I end this video then, it might be relevant for us to look a little bit at what this molecule actually looks like, because what we sometimes forget when we look at these sort of structural formulas like this, we forget the geometry of these particular molecules. So if we look at, briefly for a moment, at how this molecule is actually kind of constructed, we would know then that the carbon has a tetrahedral geometry, and we have the methyl groups are coming off here. Maybe we have the hydrogen back there. It doesn't really matter where we put these things, but except for where we put the chlorine. Now, even with this picture, you can see that there's going to be an area here where the OH, the nucleophile, has to approach from this direction, right? Because it's attracted to this positive charge here, and this is negative charge here, right? It's attracted to this one. But even with this picture, it's hard. You have to you get a wrong impression, because when you look at the actual sizes of the atoms involved, you realize that this picture, even this picture, is a simplification of the actual geometry, because the chlorine atom is actually quite large compared to the carbon. It has a much larger radius, and so the carbons that are attached here and the methyl groups, even I'm going to draw the sticks, but I can draw it like this too. It's going to be straight, and the hydrogen is going to be just a tiny little thing here, right? And so anytime the OH wants to approach this particular molecule, it's going to be repelled by this really large chlorine. And the chlorine obviously is not leaving by itself. So as long as that chlorine is attached to this, OH cannot approach from any other direction. It has to approach in through here, which is then going to be, by implication then, is going to be like a cone here. There's going to be a very limited sort of space where this atom can actually move in, or these atoms can move in. And that is why it's so important to remember this principle in kinetics, that a molecule has to have proper orientation. The collision will not occur just because the things smash into each other. They actually have to smash into each other in the right way in order for the reaction to occur. Okay, we'll talk a little bit more about SN2 and SN1 reactions and all of the different ramifications of them in the next video. Thank you for watching.